Hello everyone, welcome to the webinar number 3. Today the topic is power system stabilizer tuning for power system oscillation damping. My name is Bharti Jayasekara. I'm working at Manitoba Hydro International, Manitoba, Canada. The background, power system oscillations. When you consider power system oscillations, there can be two categories. The first one is subsynchronous oscillations. Typically, the frequency of oscillations are from 10 Hz to 60 Hz. Typically, we call them subsynchronous torsional interactions or subsynchronous controlled interactions. So it's a TI or a CI. Another type is electromechanical oscillations. Typically, these are from 0.1 Hz to 5 Hz. In this webinar, we are talking about the second category, electromechanical oscillations, and how to damp them using power system stabilizers. Power system stabilizer is a component probably residing in the exciter, and main function of that is to provide auxiliary signal to stabilizer input so that any oscillations within the electromechanical range can be damped. Now, there can be three types of oscillations in the electromechanical category. They are called generator local mode oscillations, which are essentially the oscillations between controllers inside the generator, the exciter inside the governor or inside the generator, or interaction of them. Then other type is interplant oscillations, which are essentially oscillations happening between close by or nearby plants. Third type is inter-area mode of oscillations. Those can happen between two set of generator groups in two areas. So today we are going to talk about how to damp inter-area oscillations. Now, the frequency of oscillations for inter-area oscillations are in the lower side of the range for electromechanical oscillations, which is about 0.1 to say 1 Hz. Now, in today's webinar, we are going to show you a case study using two-area system and show you how to improve poorly damped conditions by adding power system stabilizers to generators. First of all, let's look at some inter-area oscillations in the case study. So this is a two-area system. You can see in your left-hand side, we have two generators, generator 1 and 2, providing about 700 megawatts. And then your right-hand side, we have area number 2, where we have generator 3 and generator 4. Now, in the middle, we have tie lines connecting area 1 and area 2. In this particular case, we have about 4 tie lines. Each of them are 230 kV. And at this operating condition, you can see it is carrying about 400 megawatts from area 1 to area 2. And there are two loads connected at bus 7 from area 1 side is about 960 megawatts. And another load here at area 2, which is a larger one, is about 1800 megawatts. So let's look at different operating conditions for this particular example. Here we have 4 scenarios, scenario A, B, C, and D. Scenario A is the base case, where you can see load in area 1 is about 967 megawatts and generation is about 1300. So area 1 has excess power and that will be transferred to area 2. If you look at area 2, load is higher than generation. So interior transfer is about 400 megawatts. If you look at scenario B, you can notice the load is same, but there's a slight change in generation. Area 1 generation has decreased and area 2 generation has increased, so that power transfer from area 1 to area 2 has reduced from 400 megawatts to 150. In scenario 3, load has decreased, both in area 1 and area 2. And also, because load is decreased, generation dispatch has changed. The unit 2 from area 1 side and unit 4 from area 2 side have been out of service. So there's only one unit from each side, and you can see still the power transfer is from area 1 to area 2 is about 400 megawatts. The last scenario is scenario D. In area 1 load is same, but area 2 load has been reduced. And also you can see power transfer from area 1 to 2 has been reduced. So as the generation in area 1 and area 2. Area 2 generation is almost same as case C, but area 1 generation has been slightly decreased. So these are 4 potential possible scenarios of operation. And in a minute, I'm going to show you that case A, B, and C, they don't possess proper damping, or when you apply disturbance, they will have undamped oscillations, which make the system unstable. But the last case or last scenario is marginally stable, so they have a positive damping, but that probably needs some improvement. So in this slide, I'm showing power transfer in the interior lines. Remember, there are 4 lines from area A to area B. So we apply disturbance, which is a fault in circuit 1 close to bus 7, which is in the area 1 side, and that is stripped after a while to clear the fault. So you can see power transfer goes down in the circuit 1, and there are 3 other healthy circuits. I'm showing the second circuit power transfer. You can see after the fault recovers, system has a polydamped oscillations. So if you take the scenario A, scenario B, and scenario C, you can see the magnitude of the oscillation is gradually growing with time. So this will lead the system to instability. Whereas the scenario D in green, you can see the oscillations are damping, but it takes a little bit time to damp, more than 3-4 oscillation cycles. So we can look at what are the damping levels of these ones in later slides. So idea here is to use power system stabilizers to improve these undamped oscillations. So we call this an interior mode because power transfer between 2 areas show significant undamped oscillations. In addition, we can also show how generators in each area oscillate against each other. So first, there are 4 subplots. The vertical axis shows the frequency of a generator rotor. And you can see when the fault is cleared, generators belongs to area 1, which are generator number 1 and number 2, which are shown in blue, oscillate against generators in area 2, which is number 3 and number 4 in red and brown. So you can clearly see the speed of these generators are oscillating against each other. So when you go to scenario B, still you see some growing oscillations. Same with scenario D. And here I'm showing amount of interior power transfer. So regardless of the power transfer, you can see, there will be instabilities. If you go last case, the last scenario, now this has this is stable case, but still you can see some interior oscillations in that. Now note that in scenario A and scenario B there are 4 generators, and scenario C and D there are only 2 generators. That's why you only see 2 traces in each of these. So in an interior oscillation, generators will oscillate against each other, a group of generators. Now here I would like to show you what we are trying to achieve by tuning power system stabilizers. So the same plot here, interior power transfer for 4 different operating conditions. You see in the left, without PSS, we see these undamped oscillations, but when you add PSS for all 4 units, you see the oscillations are well damped. Within 2 to 3 cycles, they are significantly damped. So this is what we would like to achieve by adding suitable tuned power system stabilizers to your system. In order to do this, you need several software tools. Categorically, they are the time domain simulation tools such as PSSC, Digital and Power Factory, PSLF, or TSET, or PSCAD. PSCAD is a EMT software, others are RMS software. So in addition to time domain simulation tool, we also need a small signal stabilization tool. For example, SSAT by Partech Labs or NEVA by PTI or PSSC can be used. In this particular work, I'm using PSSC and SSAT for the calculations. Before tuning PSS, we have to do the eigenvalue analysis to identify the modes of oscillation and their frequencies and their damping levels. So in this slide, we are showing different modes and their damping levels. But before going there, I would like to emphasize one important point. In a practical power system, there will be a large number of states coming from generators, exciters, and all the dynamic devices. There can be a couple of thousands. Now, it is very difficult to identify the eigenvalues for all of those states. If you have a number of states, there will be a number of modes. So it will be difficult to identify all of them. What we do is we try to identify any mode which has oscillation frequency from 0.1 Hz to 5 Hz, because these are typical electromechanical range. So here what we are showing in this table is 4 scenarios. First of all, scenario A, scenario B, C, and D. In the first column you have mode number. Second column you have the real part of the eigenvalue for each mode, and third column you have the imaginary part of the eigenvalue, and fourth column you have the corresponding frequency, which is related to the imaginary part here, and this column here we have the percentage damping, and last column we are showing whether this is done for the system without applying any outage, or whether we have applied outage. Because what we are seeing is oscillations in the system after you trip line 7 to 8. So we are both analyzing both system before fault happens and after fault happens. So what you can see here is in each of these modes, in this column here, percentage damping is negative. That's because the real part of the eigenvalue is positive here. Now, if you go here, these two modes, the damping is positive. And also, I would like you to note one thing. The same mode here, which has negative damping, has the same amount of damping after you trip the line 7 to 8, and the frequency of oscillation has been slightly changed. So 0.7 is 0.68. So if you go to scenario B, you have similar situation. And if you go to scenario C, since there are 2 generators, there are lesser number of modes in the frequency range we are interested in, but you can see that mode also unstable. And scenario D, we can see that mode has positive damping, but it's about 3.8. Typical threshold is you should have damping more than 5%. So we will try to improve this 3.8 damping ratio, and also bring these negative dampings to positive side, so that we have better damping performance. Also note, all the unstable modes are closer to 0.7 or 0.8 Hz. So that's the frequency we are targeting to improve the damping behavior. Now, this slide shows the participation factor and mode shape of the for the scenario A for the poor damping mode shown here. when we have the line outage, that's about 0.68 hertz. So you can see the states which are participating in this mode, which has more than 0.1 participation factor, are shown here. So generator 3 speed, generator 4 speed, and generator 1 and 2 speed. They are the most contributing states for this mode. And you can also see the shape of the mode. Generator 3 and 4 in area 2 are oscillating against generator 1 and 2, which are in area 1. And here you see the participation factor, normalized participation factor here. So 1.83, 0.51, and 0.68. Minus is because it is oscillating against this. So looking at this, the best location to put a stabilizer is generator number 3. But a situation like that, I would recommend you put stabilizers for each of these generators, because if generator 3 is out of service, still you might have problems. So you have to put stabilizers for all 4 generators. Just before going to the tuning procedures, let's look into theoretical background a little bit. Why we do what we do. So here in your left-hand side, we have a simplified diagram of our two-area system. You have 4 generators and some interior branches and some loads. Let's say at the beginning we only want to put a passive stabilizer for generator number 2 here. So what procedure tells us to do is keep the generator 2 intact here, but other generators, which are generator 1, 3, and 4, replace them with a infinite bus. Now this is important to keep the fault level at generator 2 same or same as the original case. And we don't need to see any interactions between other generators, that's why we remove it. So when you do that, system becomes simplified like this, and we all know that we can further reduce that to single machine to infinite bus system shown in this figure here. We can analyze this theoretically and make conclusions that can apply to these 2 networks. In this slide, we are showing a picture of a small signal distribution model for single machine to infinite bus system. Let's identify the components here. Here we have the exciter, and this is the summation input junction for the exciter. And this is the terminal voltage feedback, and this is voltage error going into the exciter, and the EFD, the output voltage of exciter, and this represents the field winding dynamics of the generator. And EQ dash here is voltage proportional to DF's flux. And this is the torque going into the electrical component of electrical torque in the air gap. So there are actually number of torque components. Let's identify them. Here, this is the torque component coming from the governor and exciter and turbine, mechanical torque. And this here you can see this torque component is proportional to delta omega. So this is the mechanical damping available in the generator. This component, and this component you can see is directly proportional to delta delta. That's the angle change. So this is a synchronizing torque component, and this component is the component coming from the exciter. And this is the torque component we want to actually modify to improve the damping torque while keeping the synchronization torque more or less the same. Now this part is called a GEP block. It's because these parameters like constants like K1, K2, K3, K4, and these ones, depending on the generator exciter, and power system we are studying, and their operating conditions. So, and here you have the power system stabilizer, which essentially provide output which connects to the summation junction of the exciter, and this is here the voltage reference coming to the exciter. And in this particular case, I have selected speed input power system stabilizer. So the input for that is delta omega. Now later you can see there are different type of stabilizers you can use. This one particular is single input speed deviation input. So idea of the power system stabilizer is to provide a signal that can compensate the angle lagging happening here in this block, GEP block. So this block, which is represents the exciter and the generator, naturally has a lagging phase to any low frequency signal going here. Any frequency signal input coming here, that it will add a lag. So idea of the PSS is to compensate that lag by providing lead compensation. So what will happen is, if we fully compensate this lag here by the power system stabilizer, so any signal coming here, which is delta omega, or portion of that, will have a lead here, and the lead will be cancelled out to the lag here, and when it goes here, it will have a phase of delta omega. So we are adding, or we are changing this contribution more towards the delta omega, or we can say this torque component is in phase with the delta omega. That any torque component in phase with delta omega is called a damping torque component. So we are trying to enhance that torque component so that damping will be improved. Now let's see how we can achieve this. Our goal is to identify phase lag that can happen to a signal coming from here when it goes here. For the frequency range, we are interested. So let's say 0.1 Hz to 5 Hz. Now, how do we estimate this? One way is use a small signal estimator tool like SSAT or NEVA to estimate it. In that, how we do it? We apply 1 per unit disturbance here in non-frequency, say 0.1 Hz. And we measure what is the torque component in the air gap torque here at this point. Now, if we do that, if there are any contributions coming from these, then we can't identify the input-output relationship between here the output and here the input. To negate any contribution coming from these, what we do is we increase the machine inertia to a large value. Let's say 1,000 per unit. So any torque component coming here can't change the speed here, speed change here, because very large mass. Then delta omega and also delta, they both become 0. So what will happen is this path won't contribute anything, and these paths also not doing any contribution, same as here. So this will isolate these other inputs to the GEP system. So when we do input here, we can measure, if we measure the air gap torque, then we can only measure this contribution. So we want to identify the phase characteristics of that contribution. So let's go and see how we estimate parameters for the PSS. Now, for that, we need to have a stabilizer. And there are different type of stabilizers, as I mentioned before. Single input and dual input stabilizers are common to have. And again, input can be various quantities. It may be rotor speed deviation, it may be bus frequency, generator electrical power, generator accelerating power, that's the difference between electrical and mechanical power, and bus voltage. Now, in this scenario, we are using a single input speed deviation stabilizer. Here you see the model page from PSSC documentation, speed sensitive stabilizer model called step 1. This is IEEE recommended model. It's a very simple model. It has 7 parameters you need to tune. So the gain, time constant for the block here. This is called washout filter. Idea of this washout filter is to so that only pass high frequencies to the stabilizer, so that any changes happening in the power system are not passed to stabilizer. So stabilizer will not respond to any slow changes. So this filter has a cutoff frequency of probably 0.1 hertz or even less than that. Very low frequency cutoff frequency. So only frequencies more than 0.1 hertz are passing here. That's why it's called washout filter. And here we have lead lag block 1 and 2. So 2 blocks. Typically, one of this lead lag block can provide about 50 degrees of lead compensation. So when you have 2, you can probably get about 100. And finally, we have this PSS output limiter, and this is important so that stabilizer output doesn't saturate the exciter input. Now this is important when there are exciters without very large gains, but you have to carefully select some values for stabilizer output, and that can be done through trial and error simulations, time domain simulations. So goal here is to find parameters for these, which I essentially mark here, and let's see how we can do that. Here, what we are showing is the frequency lag we talk about for the GEP block. Now, again, these characteristics depending on the generator, exciter, and the power system and the operating condition. So I have picked a scenario A, and we have estimated the phase lag characteristics for all 4 generators. You can see in the vertical axis we show the phase lag. That's negative sign showing the lag phase, and horizontal axis we have frequency. So about 0.1 hertz to 5 hertz. Before going further details, I would like to mention something here. Typically, this starting point, the lag is about 60 hertz for most, so 60 degrees for most of the units I have seen. But this particular example, it is starting here. It may be a situation for the parameters we selected for the generator. This might pose some challenges. Maybe you'll see later on. But typically, it might be high value. So we know what is important is 0.7 hertz. So we need power system stabilizer to provide some lead compensation so that this lag about 40 degrees can be compensated. But if you fully compensate this lag, then the torque component going from the exciter can be totally damping, and we might impact the machine's ability to keep the synchronism because we reduce the synchronizing torque. So rule of thumb is you don't compensate fully, you compensate probably keeping about margin of 20 degrees. So you do under compensation, keeping margin of about 20 degrees. Now here in this graph, I'm showing same horizontal axis frequency, but vertical axis we show the phase magnitude. So here I disregard whether it's a leading or lagging, but I want to tell you this GEP block or generator block characteristics, like earlier we saw as the lagging or negative, now become positive because we disregard the sign. So this is a lagging characteristics, and this is characteristics of the PSS entire PSS, but we know this is a leading phase. So really, if you fully compensate, they should cancel out. But as I said, we keep a margin here, so you can see throughout this range we keep a margin. So we undercompensate to keep sufficient synchronous torque. So here we are showing the parameters we selected for the washout filter and lead lag block. So two blocks are identical, and that will provide this phase lead characteristics. And you can see the cutoff frequency we choose about somewhere here, so that this phase lead characteristic doesn't go above the lag characteristics here, so that we don't do any overcompensation. So you have to be careful not doing overcompensation. If you do, system might go unstable because of lack of synchronous torque. In this slide, it's very identical to the slide I showed at the beginning, same modes, but now you can see everything green. That means all the modes become highly damped. So you can see, the negative damp modes become positively damped, and we have damping a percentage of about more than 10. Typical target is about 5. I just did a bit more overcompensation to show the difference, but typically we target about 5% damping. And also you can notice the other modes in the same frequency range has increased that damping coefficient. So everything is very much damped. And then I want to show you the time domain simulation. So here you can see again the same contingency or same disturbance, but we have very heavily damped oscillations. This shows a healthy system with enough damping. So here we add power system stabilizer for all 4 generators. I think with that I would like to conclude the presentation. Thank you for your time. I think we have a couple of questions. The question number 1, I think, is about how we define damping percentage. Damping percentage can be defined as the ratio between 2 successive oscillations. So if we take a plot here, let's go to an unstable situation. So if I take this successive peaks, let's say these 2. So the first peak minus second peak, and you take log of that. But the point is, it's a ratio between first peak. I'm sorry, I have to correct myself. It is the log of first peak divided by second peak, and because you take the log and there's a number less than 1, in the case of negative damping, it will be a negative number. Now if you go here, first peak and second peak, the ratio between first peak divided by second peak is more than 1. So log of that would be a positive number. So that's how when the magnitude goes down, that's how damping become positive, and when the peak is going up, that's how damping become negative. And also I have to mention, it has a really good connection to the real part of the eigenvalue. Eigenvalue for a oscillatory mode is a complex number. Eigenvalue for the asymptotically damped, which is not oscillatory, but asymptotically damped mode has only real number. That's an oscillation. So the real part of the eigenvalue is actually Napier's per second. That indicates the amount of damping. There are 2 more questions. I think slide 19. The question was why we use 0.7 Hz. I think that's a very good question. The reason because if you go one level, a few levels up, actually here, you can see all the negatively damped modes have a frequency closer to 0.7 hertz or 0.8 here. So frequency of interest, where we want the power system stabilizer to provide leading phase, is about 0.7 to 0.8 hertz. But that will impact all the modes in that frequency range. So that's why we also plot other modes in the frequency range. And later in a later slide, you can see the damping of all these modes has been increased. In this slide, we can see, still the modes have very similar frequency levels, but damping of all those have been increased. So objective was to increase damping from negative value to positive, sufficient positive value for these 0.7 hertz modes. There's another question. Do you see the significance of using global signals in PSS instead of local signals? So that's a good question again. Whether we use local signals or global signals or wide area measurements, I think that's what you are probably targeting. I think I only show the classical definition of PSS, and at the very beginning, that's how it evolved. People use local signals, but there were some global signals like frequency. But today, there are more sophisticated power system stabilizers, especially for interior modes. You can do the measurements, global measurements or wide area measurements, and provide feedback. But there you have to be careful with the signal delays. So there are practically in that signal delays how they can impact. But since the oscillation frequencies are very small, and today communication is very fast, you can use them. And I have seen a few instances they use global signals for interior oscillation damping. So another question, I think question is about what is the individual effect of inertia and damping. Can you look at it separately? I think let's go to answer this question. Let's go to the theoretical side here. Now, inertia is whatever the torque coming here. That's the difference between the mechanical torque and some of electrical torques. We call acceleration torque for this component. The acceleration torque, when it's provided, how much speed deviation we have is defined by the inertia. The m is 2h, h is inertia constant, and if h is large, you are less sensitive to torque changes. So, or in other words, you have in the rotor mass you have more stored energy if the h is large. So you will dissipate more energy before you slow down. On the other hand, for a same amount of energy difference or power difference, your delta omega is lower if the inertia is large. So inertia has an impact how fast your frequency change for same disturbance. Now, whereas damping is different situation. Damping for same inertia, damping provide it is the phase of the torque, the resulting torque here. Whether what is the same magnitude of the torque? It may be same magnitude, but it is the phase of the torque. Whether that is with the in phase with the delta omega, then we call damping torque. If that is in phase with delta delta, we call synchronous torque. I think it's hard to compare and contrast these two contexts because they are two different things. But impact of inertia is reduce the delta omega for same power mismatch or same acceleration torque or acceleration power. Plus damping, I think we should talk about synchronizing components of damping and damping components of damping. So if we have proper damping component, but if you don't have synchronizing torque component in the machine, what will happen is at the first swing, machine might lose the synchronizer. So that's a situation where you have poor synchronizing torque component, whereas you have you might have good damping torque components. Now, other situation, I think what we saw here, we didn't see anything going unstable in the first swing. Let's go back to them to explain that further. So here, this has enough synchronizing torque, the torque which is proportional to the delta delta. So that's why when there's a actually this is I'll show you a angle plot which I don't have right now. Let's assume this is the generator angle. You have seen this kind of oscillations. Let's assume these are all generator angles. So when the angle deviates, it comes back because of the sync torque. But in this situation, it comes back, but it gradually keep on growing. That's because you don't have damping torque component. So synchronizing and damping torque, that's how it works. So if you have poor synchronizing torque, it will go unstable from this point. At this point, it goes unstable. I'm sure you have seen such situations. Very likely the first swing or second swing, it might go. Very likely first swing, it goes. But gradual increase in the magnitude of the angle means you have insufficient damping torque. I think I adequately answered that, but if you have questions, we can discuss that later further. Then we have another question. If we tune our stabilizer to 0.5 hertz, what range it will be good? Now here target was a 0.7 hertz, but we look at 0.1 hertz to 5 hertz. In reality, you had to look at even a wider range of the impact. Poor tuning of positive stabilizers can make other problems, such as you might have torsional oscillations having poor damping because of you install a power system stabilizer to mitigate electromechanical oscillations. So here, that's why we analyze, even though we did for like 0.7 hertz somewhere here, we analyze for whole range. Now, in addition to that, here we look at again 0.1 hertz to 5 hertz. Now, I think it's very important to check the behavior of the system after installing power stabilizers for wider range of frequencies, because your PSS doesn't only it doesn't only provide this lead compensation for the frequency you need. You can see the trend here is going down, but here is going down, but it will go for a wider range. So if you look at 60 hertz, the power frequency, still there might be some contribution coming from the PSS, and it might have other impacts because of that. And typical known situation is if you improperly tune stabilizers, it might make some torsional issues in higher frequency range. So you might see some torsional interactions, or it might have situations, I haven't seen those, but it might have situations, it might negatively impact some SSCI control interactions. Typically, when you do that for the generator, it's unlikely because generator is a huge mass, and only thing we have seen is it might impact your torsional oscillations. So we use eigenvalue tools, which are essentially linearized tools. That's why we have to look at a number of operating scenarios. My rule of thumb is when you tune a PSS, then you check the performance in time domain simulations to check the behavior. So it can be RMS simulations like PSSC, and also you might want to check similar situation like EMT tools like PSCAD or other EMT tools to see whether there are any negative torsional impacts. We have another question. When you simplify, the question is, when you simplify system like that to, one machine defined by system, we lose, information regarding inter-area oscillation mode. And that's a correct comment, but I think we have to see objectively what we are trying to do here. Here, the reduction of the model is just to identify the phase lagging characteristics of your system. That's the only objective, so that we can use PSS to compensate that part. So after that, you look at entire system. I want to emphasize this. When you come to this eigenvalue analysis, this whole entire system, and then when you do this time domain simulation, this again the entire system, and you see the effectiveness here. Now, having said that, I want to say that today what we present is a traditional method of tuning power system stabilizers. There are other methods. Especially, I want to mention the method based on the residues. In that, we can do a more detailed eigenvalue analysis using whole system. Those are more advanced methods, and there are other methods proposed in literature. But the traditional method is very effective. The main challenge is in tuning is how you have robust tuning that would work for many different operating conditions and also system configurations. You might have certain units in service, you might have some lines out of service or in service, like that. So sometimes same set of parameters doesn't work all these conditions. So then you might need some adaptive control, meaning you might have different set of parameters for different situations. But going back to the question again, I think OMIB, or one machine to unified bus system, only used to identify the frequency lag characteristics of a unit, so that we can compensate that part. I hope I answered adequately. I think that will conclude the questions we have. I think thanks for your time and for your attendance. If you have any questions, please let us know. We'll try to answer them, as we can. Thank you very much again.